So it's going to be a gentle introduction for the reporting deleterious germline variants in hematological disorders. Sorry? This one? Okay, thank you. And I think we are always focusing on the somatic mutations when we are dealing with hematological disorders. And today there will be a special focus on the germline. This slide presents the workflow or the timeline for the germline mutations when it's affecting or happening at the sperms and eggs, then into the zygotes, then affecting all cells in the babies and inherited to the next generation. Unlike the somatic mutation, where it's happening after the zygote stage, affecting few cells, and usually is caused by environmental factors with some predisposition in germline, and usually is not transmitted to the next generation. So in my talk, in 15 minutes or so, we'll be talking about what's the germline mutation landscape. We'll discuss some reporting guidelines, and finally, we'll see how this comes together as a workflow. So how important is germline mutation and how common it is? So there are some studies in the recent years that says it's 1 in 12 patients that will come to the clinic with a germline component, up to 1 in 6, which is really high. So let's see one of the first big studies that's happened in this space in St. Jude Children's Research in 2015. They basically sequenced more than 1,100 patients using whole genome and whole exome sequencing data. And they found across different tumors in young patients younger than 20 years old. And they found it's a germline mutation in 8.5%, which is 1 in 12. If you look at this figure, you will see there's so many different cancers involved. Some are solid tumors. But on the top right side, the leukemia represents 25%, Hodgkin lymphoma 7%, non-Hodgkin lymphoma 6%. So this is really a big number, almost 40% of the patients, young patients with tumors have a germline component. And if you say, this is too big, let's just focus on the patient that comes to our clinics with a hematological malignancy, and we want to see if they have a germline component. So this is a smaller study where they have 67 patients referred to hereditary hematological malignancy clinic, and they found 12 patients representing 18% or 1 in 6 patients. So clearly germline mutation is a big component and to be expected in many of our patients. So when to suspect a germline component? Of course, the personal history and the family history is a big part. For example, cytopenias with excessive toxicity with chemotherapy or radiation, if there is multiple kind of cancers in the family or multiple affected or usually unusual age for the presentation, or with the physical examination when you see these morphological features that will give you clues on the germline component. And this table will show the breadth and the spectrum of different components. For example, in the Elaine gene, beside the neutropenia, we expect to see some skin and the growth features. In the GATA2 gene, beside the anemia, neutropenia, we also expect to see immunodeficiency. And the hematological malignancy that comes with with these genes, could be bone marrow failures, MDS, AML, or lymphoma. So it's across the spectrum. And not only that, they come in different flavors: autosomal dominant, autosomal X-linked, autosomal recessive. So clearly there is a huge spectrum of germline mutation affecting hematological disorders that need to be paid huge attention for the patient and their families. So what are the methods that we should use for germline mutation? With different variants, we expect to see different, there is many biomarkers. Most important ones and most common is the single nucleotide variants, followed by insertion deletions, copy number variants, structure variation like gene fusions, and clonality. And for each biomarker group, there is a method that is optimal for detection of that biomarker. For example, real-time PCR is good for point mutation, insertion, deletion, and fusions. Capillary sequencing or Sanger sequencing is mostly for the first two. But we have FISH, we have MILPA, we have arrays, and we have next-generation sequencing, which has the promise of actually detecting all kinds of biomarkers in theory, and it's proving to be very valuable. Now the question is, what is the tissue to confirm the germline mutation? So blood is definitely not helpful here because it's a cross between the cancer itself and the germline. So we wouldn't know which one is which. So it's not helpful for confirming the germline, but it can be the starting point. Buccal swabs is good, but unfortunately, it's sometimes contaminated with WBCs, so it's not going to give you a definitive answer. So it's not the best sample type to confirm germline. Hair follicles is great. It's not that invasive, but very difficult to actually extract DNA in the laboratories, given that how small is the specimen. So it can be used in highly developed and advanced labs. Finally, is the gold standard is the bunch biopsy, skin biopsy, basically. It's a little bit invasive, but actually this is the golden standard to confirm germline mutation in hematological disorders. So coming to the second part. So if we have a mutation, how do we report if it is deleterious or not? How do you trust my opinion versus Dr. Musa's opinion versus someone else's opinion? So we have to have a guideline. And the gold standard here is the Acmg Guidelines, the American College of Medical Genetics, published in 2015. And there is a barcode here to scan it for reference. It's very extensive. They came up with an extensive criteria to classify variants. And as you see, I'm not going in any details here, but for pathogenic mutation, for example, they have criteria. If the evidence is very strong, strong or moderate. If I zoom in the very strong evidence, it usually starts with loss of function. Truncating mutation, frame shifts, usually considered very strong evidence. And then they develop this even in a similar way, where, for example, you have the benign section, the pathogenic section, and how the evidence will support this side or that side according to many criteria. The first one that I will only talk about is the population data. So how common is a mutation in the databases for whole genome or whole exome? If it is very common, as you expect, it will be strong P9. If it is very rare, the evidence will be stronger. So what is the database that we usually use, or what is available now? Many of them. But I will just mention one of them called NOMAD. This is an amazing database with almost 100,000 plus whole genome and whole exome. It's freely available. You can search for any gene, any mutation, any location. And it contains so many different populations around the world. For example, you see how they are related to each other. The orange is the South Asian. The Swedish is the purple, Finnish, Ashkenazi Jewish, Latino, Korean. Unfortunately, Middle Eastern is not well represented in this, but this will change, inshallah, in a couple of years when more data is being poured in this database. When you look for one gene, for example, you will see this interface. The black barcodes is the exons, and each exon will represent how good is the coverage across the 100,000 patients. And if you zoom in more, in one of those exons, you will see a list of mutation. Each row represents one mutation with a classification, pathogenic, likely pathogenic, etc. And if you click on one of them, then you go into the deeper resolution. How common is that mutation in different population? You see, for example, here, the allele accounts in different population. We found 20 alleles across 100,000 patients. And then you see there is none of them have a homozygous mutation, which tells you that this is a very rare and probably important mutation. And the allele frequency is extremely low. So if you see a loss of function mutation in this database, and it is as rare as this one, then the evidence becomes very strong. So when we use Acmg guidelines, Sanger sequencing, NGS, how does all of this come in a workflow in reality? Usually, bone marrow in the lab, at least, the workflow starts with the bone marrow initial workup, morphological assessments, flow cytometric and immunophenotyping, cytogenetics and FISH, and molecular studies. So all of this usually starts with the bone marrow biopsy. And assuming that the current practice is use NGS, and the NGS panel is big enough to have predisposing genes, then we are going to look for a mutation with VAF above 0.3. What is VAF? VAF is variant allele frequency. If it is above 30%, then we suspect it's a germline. It's not a final answer, but it's suspicion. So we will go for a skin biopsy in order to do a comprehensive germline testing. So let me focus back on allele frequency. What does that mean? When we do NGS, for example, Illumina platform, and we are sequencing millions of reads, we end up having thousands upon millions of short DNA reads. And the first step we do is we don't know where they're at the genome. So we have to map it. So a program will go and take every read and start screening and mapping it to the genome. It will do this for all the reads. And then once it's organizing every read, where does it fit in the genome, another software will come and do the variant calling. It will start screening vertically, looking for difference between the reference in red and the reads in black. And you'll see here the reference there in red is A, and there is C, A, C, C, C. So we are looking at a change from A to C at that position. If we suppose there is 100 reads covering this region, and the normal allele is 55 reads, so this is a 55% allele frequency, and the C is supported by 45% reads. So this range tells us that it could be a heterozygous, 50% from mom or dad has been inherited. But it could be also somatic. We have no way of knowing which is which. But if this is very low, like 5%, 10%, this is unlikely to be inherited because the germline usually between 50 and 100%. Anything below that is usually somatic. So in that case, we go for a skin biopsy, we do the germline. The other way of approaching this is if the clinical history is so strong, the patient comes with a personal history of 2 or more cancers, young age, or strong family history, so we can go directly for a skin biopsy. And if the germline testing show deleterious mutation, then surveillance will follow, segregation study in the family, and assessing the related donors for familial variants. So with that, I hope that I was able to describe when to suspect a germline component and how important it is currently. What are the methods used? NGS is the gold standard and confirmation by Sanger sequencing. Tissue is, buccal is not optimal. Skin biopsy is the gold standard. Guidelines for interpretation is the Acmg 2015 guidelines. And the GNOMAD is one of the most important databases that we have free of charge with 140,000 whole exome and whole genome. Thank you so much for listening.